Hello calculus students, here we are with our last section in chapter 8, log functions and integration. So first of all, let's review the integration we had so far with the power rule. As you recall, integral of x cubed, you crank up the power 1. So it's x to the 4th over 4 plus some constant integration. X squared would be x cubed over 3 plus some constant integration. X, which would be x to the 1st, would be x squared over 2 plus some constant integration. Even x to the 0 would be x to the 0 plus 1, which would be x to the 1st over 1 plus some constant, which is basically x plus c. Remember, the antiderivative dx is just x. But what do you do with this when it's x to the negative 1? That would be x to the negative 1 plus 1 over negative 1 plus 1. That's x to the 0 over 0. Oops. This does not work. For a power n equal to negative 1. We have to do something else to do the integral of dx over x. And that's what this section is all about. Because we have a derivative of the natural log being 1 over x, then we can do the antiderivative of the natural log. And that's what we're going to do here. Notice that this is the power we were trying, and it doesn't work if n equals negative 1. So here you go. Integral of 1 over x dx equals the natural log of the absolute value of x plus c. And the same thing if we do a general function u. Notice the absolute value on there. You've got to do that because if x is negative, you're going to take the natural log of a negative number, and that's not real. So you can also write it this way and put the u prime over u. So the du over u, and look for a derivative of the bottom function on the top. This pattern is going to come up over and over again. So using the log rule for integration, 2 over x is 2 times the antiderivative of 1 over x dx, so you get 2 natural log of x plus c. Or you can write the 2 inside with a rule of logarithms. And you don't need the absolute value anymore because x squared is always positive. Now let's try this example. Use the log rule for a change of variables. Well, we let u equal 2x minus 1. That's the thing underneath. So du is 2 dx. So all we need in this thing is to sneak a 2 in here. So we'll put a 1/2 out here. So 1/2 integral of 2 dx over 2x minus 1. So 1/2 the integral of, or antiderivative of du over u. So that's 1/2 the natural log of the absolute value of u plus some constant, or 1/2 the natural log of the absolute value of 2x minus 1 plus c. Now if you want to, you could sneak the 1/2 inside as a square root. So, or natural log of the square root of the absolute value of 2x minus 1 plus c. Now let's find some areas. Find the area bounded by the graph. X-axis, the line x equals 3. So we want to find this integral from 0 to 3 of x over x squared plus 1 dx. Well, integral from 0 to 3 of x over x squared plus 1 dx. Let's let u equal x squared plus 1, the bottom function. So du is 2x dx. So we do have to sneak in a 2 here, and a 1/2 outside. And also, we're going to change our variables. We're going to also change our limits of integration. So if x is going from 0 to 3, u will go from, put in 0 up here, 0 squared plus 1 is 1. 3 squared plus 1 is 10. So we have 1/2 the integral from 1 to 10 of du over u. So that's the natural log of the absolute value of u evaluated from 1 to 10, and let's not forget the half out there. So 1/2 times the natural log of 10 minus the natural log of 1, which is 1/2 the natural log of 10 over 1, or 1/2 the natural log of 10, or natural log of 10 divided by 2. Let's check this on our TI-89. where you do antiderivative, left parentheses, the integral of x divided by left parentheses x raised to the 2 plus 1, right parentheses, comma, x going from 0 to 3. See if we get the same answer. And yes, the TI-89 agrees. Natural log of 10 divided by 2. Okay. Now, recognizing quotient form. So here's a bunch of problems just where you have to recognize when the top is the derivative of the bottom. And then you can use this natural log antiderivative rule. So here, x cubed plus x, if you take its derivative, you get 3x squared plus 1, which is what we have on top. X squared plus 2x, the derivative is 2x plus 2, and that's what we have on top. We had to do a little prepping for first the 1/2. 3x plus 2, the derivative, du, is 3. So that's the technique. Now here's another trick using long division before integrating. So what we're going to do is first divide this out long end. Fortunately, we can't use synthetic because it's an x squared. But I think we still got those skills, right? X squared plus 1, put it into x squared plus x plus 1. So we can get x squared and x squared is 1. And we get x squared plus 1. When we subtract, you just get an x left over, and we're done already because this remainder is a lower degree than x squared plus 1. So we rewrite it as the integral of 1 plus x over x squared plus 1 dx. And so it can be the integral of dx plus the integral of x dx over x squared plus 1. Well, this one's ready to become 1 plus, here we have to do a little prepping because if the bottom is x squared plus 1, we want the top to be the derivative of the bottom. And notice we just pop a 2 in up here and a 1/2 out here. Now we've got it. Now it becomes 1/2, and we can go to the natural log of the absolute value of x squared plus 1 plus some constant integration. Now notice this 1 is a constant and this is a constant, so you can just kind of blur them into the same constant. And also the natural log of x squared plus 1 is positive. X squared is always positive and you're adding 1 to it, so we don't really need the absolute values. So you could just say 1/2 natural log of x squared plus 1 plus your constant integration. The 1 constant here got merged into the general constant. Or you could put in the 1/2 as a power inside and then turn it into a square root. Natural log of square root of x squared plus 1 plus some constant. And again, you can check these on your TI-89 as well. With the integral symbol, just don't put the limits of integration in. X squared plus x plus 1 over x squared plus 1. Left parentheses again, x squared plus x plus 1 divided by x squared plus 1, comma, x. Just stop there. Okay, and this is why it helps to look at things on the calculator, because the calculator agrees with me. Natural log of x squared plus 1 over 2, that matches with that, but then it says plus x. It forgets the constant integration, and I forgot something key over here. Antiderivative of dx is not 1, it's x. Let's get that fixed. So we don't merge that into the constant at all. So we got to make our plus x here all the time. X plus, or x plus the natural log squared of x squared plus 1. Okay, sorry about that. We found a mistake by checking. Now let's do a little change of variables with log rule. Okay. Notice how when you take this derivative of x squared plus 1, you get 2 times x plus 1 up here. So that's going to be a schmite big trickier. But it might be very easy if we just let u equal x plus 1. So if we just let u equal x plus 1, then x equals u minus 1. And du equals dx. So we can change this to the antiderivative of 2, and x is u minus 1. Dx we see as the same thing as du. And x plus 1 is u squared. So antiderivative of 2u minus 2 over u squared du Now we can distribute the division over subtraction. So we get 2 over u minus the antiderivative of 2 over u squared du. One of these requires the log and one doesn't. And that's basically this one here. 2 times antiderivative of 2u over u minus 2 times antiderivative of u to the negative 2 du. So here we use our new idea of natural log of the absolute value of u. Here we can use just the old power rule, u to the negative 1 divided by negative 1. And we can use one constant integration for both. So we end up with 2 times the natural log of u, which is x plus 1. Keep the absolute values on there. The negatives cancel here, plus 2 over u, and u was x plus 1 plus c. Let's do our TI-89 check on this one too, just because I've been known to make mistakes. I checked this on the TI-89, and I think I'm even now, because the TI-89 goes 2 natural log of x plus 1 plus 2 over x plus 1. Of course, it forgets the constant integration. But note this. TI-89 doesn't know about that absolute value restriction on the x plus 1. So, because I asked it what the integral of 1 over x dx is, and it said natural log of x. So that's wrong. It should be the absolute value of x. So keep that in mind, that the TI-89 is a little lax on that, and it should have absolute values on those the arguments inside. Unless, of course, you know that the argument inside the natural log is positive, but not in this case. Okay, so here's some guidelines for integration now that we have so many rules. And there's that computer software helping out here. And now we're going to do use substitution in the log rule. Solve this differential equation. Oh, Neller. And we got another one like this too. And an application. Okay. So 1 over x natural log of x. Solve the differential equation like that. Okay. So we get dy equals dx over x natural log of x. And so we take the integral of both sides, integral of dx over x natural log of x, and we get y equals the integral of dx over x natural log of x. Now, well, what do you do with that stuff on the bottom like that? Well, the derivative of the natural log is 1 over x. And so we'd have it right there. If you let u equal the natural log of x, then du is 1 over x dx. And so we can replace our original expression as y equals the integral of dx over x becomes the du times 1 over the natural log of x, which is u. So we get the integral of du over u. We know how to do that. That's the natural log of the absolute value of u plus a constant. And now just put in what u was, which was natural log of x. So it's the natural log of the absolute value of the natural log of x plus c. That's bizarre. Let's check that on the TI-89. TI-89 agrees. Again, it forgets the absolute value in here. And a natural log can go negative if you go less than 1. Natural log of 1 is 0. Natural log of a half is, yeah, 1 over 8. So here we go. Use substitution in the log rule. Another one. Hello. 1 over square root of x plus 1. These get to be some doozers. Well, let's give it a try. Let's let u equal square root of x, in which case du is 1 over 2 square root of x dx. I don't see that working out so well. I think usually with u substitution you want to make it the whole thing square root of x plus 1. Okay. And so du is 1 over 2 squared of x dx, and then that 1 disappears. The problem is coming up with this extra square root of x in there, but I think we have a solution for that. We have the integral of dx, and we can call dx du times 2 square root of x, and I think it's coming now, people. We replace the dx with 2 times the square root of x du, all over now square root of x plus 1 is all of u. And now we can use this rule again to make another substitution, because square root of x equals u minus 1. So the integral of 2 times u minus 1 du over u. Now we're getting somewhere. So now you get the integral of 2u minus 2 over u du. So it's the integral of 2 minus 2 over u du. The integral of 2 du minus the integral of 2 du over u. So this just ends up being 2u minus 2 times the natural log of the absolute value of u plus your constant integration. And now you can unsubstitute. So it's 2 times the square root of x plus 1 minus 2 times the natural log of the square root of x plus 1. Notice I don't need absolute values in this case because x has got to be positive in the first place to exist, so that we don't have real answers. And then we're adding 1 to it. So the output of the square root is positive. If you add 1, that's still going to be positive. Plus c. And actually, if you go a little further on this, because if you distribute the 2 square root of x plus 2 minus 2 natural log of square root of x plus 1 plus c, these are both constants. So I can merge this in with a constant term to say just 2 square root of x minus 2 natural log of the square root of x plus 1 plus the constant integration. And let's check the TI-89. And hooray, the TI-89 agrees. Okay, now here's an application problem. As the volume of gas at pressure P expands from V0 to V1, the work done by the gas is that integral. The quantity of gas with initial volume of 1 cubic foot and a pressure of 500 pounds per square foot expands to a volume of 2 cubic feet. Find the work done by the gas. Use the pressure. That pressure is inversely proportional to the volume. Okay. Well, because P equals K over V, and P equals 500 over V equals 1, K equals 500. So they came up with that way. So the work done is given by this integral. And isn't that handy? We just learned how to deal with 500 over V. It's the natural log of V. So there you get about 346.6 foot-pounds. Now, occasionally integrand involves an exponential function with other than e. And to do this, we can use those rules we talked about. So integrating a function to another base, so the integral of 2 to the x dx, we can just say that this is going to be, using the rule we just looked at over here, 1 over the natural log of 2 kind of as a correction factor, times 2 to the x, plus the constant integration. And that's fine, you can leave it like that. And ready for the exercises. Notice there's not a lot of application problems in here. Well, there's a few. You might have to see one. Here's a step-in integral. Okay, flange out.